In this lesson, we are going to look at just a brief introduction to light and reflection. So light and reflection. Okay, so if we think about light, for example, so light can, the way to kind of think about it is you can think about it as a particle, okay, which is known as a photon. Or you can think about it as a wave. So it's like this. And this is what's known as the wave-particle duality of light. So you can think about it as a wave, or another way to think about it is as a ray. Now, light is a member, or what it is from a scientific point of view, it's what's called electromagnetic radiation. So what we have is we have something like this. So this is what's known as the electromagnetic spectrum. So all that really means is that, so if we have a look here, so we can see that all of this electromagnetic radiation is, when we look at it as a wave, we can see that, so you have your wave, and what you have is you have your wavelength, okay, which is the length of the wave, and then also then you have what's known as the frequency. So if you pick a particular point, and it's how many wave cycles past that point, that's what's known as the frequency, or how frequent it occurs. So if we have a look here, so there's all different types of electromagnetic radiation. So let's say at one end you have radio waves. And if you have a look here, you can see that the wavelength of radio waves is fairly spread out. And the frequency is isn't as high if you like. Okay? There's not going to be as many of these radio waves passing this point every second. Now as you move this way, you can see here that the wavelength decreases and the frequency increases. So you can see when you start to get up here, for example, on the extreme end you have gamma rays, and gamma rays are high frequency, low wavelength, and they are they have a lot of energy, and they're very penetrating, and they can actually be very damaging to the body. Now some are then in the middle here, so between infrared and violet. So let's say, so here we have what's known as visible light, and this is kind of the light that we're going to focus on. So this 700 nanometers, 500 and 400 nanometers, that refers to the wavelength, this here that we've been talking about. So it's the length of the wave. So you can see that each color has a specific wavelength associated with it, and that's kind of like what distinguishes one color from another. They're all electromagnetic radiation, but the wavelengths are slightly different. So you can see here there's a difference between these wavelengths. So longer wavelengths then, so let's say down here, so let's say so the color red, for example, is a longer wavelength in comparison to the other wavelengths. They are low energy, and the shorter wavelengths are higher energy. So the way to kind of think about it is, if you think about a body of water, for example, and this is the side of a, let's say, like land. If you have, let's say, big waves that are like this, they just move along, just kind of bounce off and then bounce back. There's not a huge amount of energy. But if you have, let's say, like you have the same kind of body of water, but you have these very steep waves like this. These waves, so these wavelengths are much shorter. They're much shorter, and they're going to have more of an impact on, they're going to carry much more energy. There's going to be higher energy, and when they impact, let's say on the side of the coast, for example, they're going to impact and put more energy into the coast like that. So that's one way to kind of think about light, and to think about as a function, as a wave, okay, as a wave. Now Light is so we can use this light. Light can travel through a vacuum. So what does that mean? So if we think, like, let's say this is the Earth. So this is our Earth. And then around the Earth, then we have the atmosphere. Okay, and there's loads of atoms inside this atmosphere. And generally it's nitrogen, hydrogen, oxygen, and CO2. So atoms, as we know, is made up of matter. So the matter that's up here, it's in gas form. So what's happening is you actually have light that's traveling through and moving through this atmosphere coming from the sun. So imagine the sun is out here. And these wavelengths, these rays of light, or waves of light, or you can think of photons of light, are traveling through space. And space is a vacuum. So what that means is that the space between, let's say, the sun and the earth, so this space in here, if you were to look in this space here, it's a vacuum. So it's actually a vacuum. And what that means is that there's no matter in here. There's no air, there's no atoms, it's just space, just an empty space, which is a vacuum. And light can travel through a vacuum. It doesn't need a medium to travel through. If you take sound, for example, sound needs a medium to travel through, whereas light doesn't. Light can easily pass through a vacuum. Now, light travels, these rays of light can travel, and they're very, very, very fast. In fact, the speed of light and sometimes they use this small c to represent the speed of light. It's insanely fast. So it's 3 multiplied by 10 to the power of 8 meters per second. So if you imagine, imagine this 3. So imagine, so it's 3. So it's essentially, if you think about it, it's 3 with 8 zeros after it. So it's 3, 0, 0. That's 1, 2, 3, 4, 5, 6, 7, 8 meters in every second. That's how fast it actually travels. So it covers this distance in 1 second. So think about, if you just click your finger, that's roughly 1 second. Light, a ray of light, or a wavelength, or a wave of light actually travels that distance in that second. So it's insanely fast. So it's actually the fastest, light is the fastest known velocity in the universe. So there's nothing that we know of that we're aware of that can actually travel faster than light. It travels insanely fast. And light, also another way to kind of think about light then as well, is that light is a form of energy. So energy is the ability to do work. So, and you can really notice that as well. Like if you take your hand and just put it up in front of the sun, you'll actually feel the heat energy on your hand. Another thing as well that you may have come across during your junior cert is what's called one of these guys, which is known as a Crookes Radiometer. So if you were to take light, so if you were to take your light source, so imagine this is a source of light. If I do it in a different color, and what will happen is this light waves will pass through this radiometer, Crookes radiometer, like this, and they'll hit these veins, and what will happen is they'll cause the veins to rotate. So what you have is you have light energy being converted into kinetic energy. So you have this conservation of energy, so light energy being changed into kinetic energy. So again, you know, light, it's energy, it has the ability to do work. In this case, it can actually cause these paddles within the Crookes radiometer to actually start to rotate. Also as well, you know, like with solar panels, so for example, solar panels, what they're doing is they're taking the energy from the light from the sun and they're converting it then into another form of energy that can be used to generate electricity in your house, which can be used then to power your house, for example, to do all of the things that you need to do in your house. So again, it is a source of energy. Light then also as well is extremely important for our ability to see. So light is very much linked into sight, and because we can see it, because we can see light, and we can detect it with the eyes, we can actually study it then as well. Now the interesting thing is that, like, as humans, we can only see with the naked eye within this band here, within the visible spectrum. So even as you sit here now, as you sit here listening to me, in the room that you're in, you have all of the different light that's bouncing off all of the surfaces all around you and hitting your eye and causing you to see the objects that are in the room around you. But also as well, there's also other, like there's going to be radio waves, microwaves, infrared and ultraviolet, X-rays and gamma rays, all passing through the room that you're in as well. But your body is not picking any of those up because your sense organs are not attuned to be able to pick up those different types of electromagnetic radiation that's passing through the room. So it's very interesting to kind of think about that. Now we can use devices so that we can actually see the infrared or the ultraviolet radiation, and we can use instruments to detect X-rays and gamma rays and microwaves, and then also like we use, for example, radios to tune in and be able to broadcast and pull down, if you like, the radio waves that pass through the air so that we can listen to them and listen to music. So that's light. Now what we have then as well is, like, we have, so for example, we have light from the sun. So this is the sun, and it passes down, and what happens is, if you have an object here like this, it hits the object, and what happens is some of the light gets reflected off and some of the light is absorbed by the material and goes into the material, and some of it bounces off, and that's what actually enables us to be able to see objects. So you have this, what's known as white light. So white light comes from the sun, and it contains all of the different wavelengths of light within it. So if we think about then, like the light that it reflects off objects. So it reflects off objects in different ways. So if we have a look at this here, let's try that again. So light can hit objects and bounce off them in different ways. The way that we will look at is what's known as reflection. So it's specular light or specular reflection, and this is basically where light bounces off an object, and we look at some examples of that. Then we have what's known as glare, and again, it's like when you have kind of like a glossy type of a surface, you get light bouncing off this surface like so. And again, I'll show you an example of that. And then the other type is what's known as scattered light. And generally, if a surface is really smooth, you're going to get reflection. If it's kind of glossy, you'll get what's known as glare. And then if the surface is not smooth and it's kind of lumpy or has grooves in it, even if they're microscopic, what's going to happen is it's going to scatter the light, and it'll scatter it like that. Now it's actually a good thing that it does scatter the light, because objects scatter light in this particular pattern, it enables us to be able to actually see the objects. it enables us to see the objects. If we can't, if it didn't scatter light like this, objects would be invisible to us. We wouldn't be able to see them. We would not be able to pick them up with the eye, with the sense of the eye. So if we think about some examples of this, so let's just look at some examples of light passing through objects. So bear with me now one sec. So if we have a look at these three objects here, so this first object, so if we think about, for example, the surface here, we're talking about the surface of the lake. What you have here is you have what's known as specular reflection. So basically you have light that's coming from, that's bouncing off the mountains and the trees, for example. It's hitting the lake. And then what's happening is it's been reflected off the lake. This light that's been, so the light, all of the light that is coming from, that's been bounced off the mountains and the background here has been reflected off the lake, and then that's been picked up by your eyes. So what's happened is an image is being formed here. But the reason why you can see the image, and it depends on how smooth the water surface is and how calm the lake is, this will determine whether you can actually see that, you can see the reflections of the backgrounds within the lake. If this water starts to get churned up, what starts to happen is you can get glare, for example, from the lake, but you can also then start to get scattered light as well, where you wouldn't be able to actually see. You can see the lake and you can see the water, but you can't actually see the background reflection from the objects that make up the background. If we have a look here, so we can see here, so see the way, so light is coming from the sun, and what's happening is it's being scattered by the particles that are in the air, and what you can see here, that's kind of like radiating out all over the place. So what's happening is you're getting this scattered light effect as well. It's important to know as well, like light travels in straight lines, and then what happens is it can when it hits an object, it can either bounce off the object or it can be absorbed by the object, depending on the material that's in the object. So that's that type of pattern. And then glare is kind of like this when you see this. So for example, even though the surface of the carbonate is black, we can see here this is appearing white. Okay, so what's happening is you're getting this kind of glare effect because the surface is kind of glossy and it's catching the light, and what's happening is you're getting a glare kind of effect as well. So this is just a way that we can study and we can look at light and look at how it bounces, how it interacts with surfaces, or how it interacts with surfaces and mirrors and things like that. Also, as well, as I was saying, the light that comes from the sun is what's known as white light. And what happens is, so here we have what's known as a prism. So you have light that's coming from the sun, and it contains all of these wavelengths. So imagine you have light coming from the sun, and it has all of these wavelengths. And what happens is, if you shine this, so this is white light, I'll just abbreviate white light, and you pass it through a prism like this, so a piece of glass, what's going to happen is the light will bend, and it'll bend, all the different wavelengths of light will bend just slightly differently than each other. And what happens then is, as a result of that, they'll come out of the prism and they'll be, if you like, split up. So that actually enables us then to see the different wavelengths of light. And the reason why we can see them is because they all have slightly different wavelengths. And as a result of that, they will all be refracted or bent inside this prism, just all slightly differently, and they'll come out slightly differently out the other side. Now, as a result of that, what happens is they split up like this. And that's like what happens with light when you, for example, when you pass it through a prism. So when physicists are studying light, they can study it in two different ways. One way uses geometry to predict the path of light rays as they pass through different materials, and this allows us to study the reflection of light in mirrors and refraction or bending of light through prisms and lenses. So we can do things like this. We can actually study it. We can study light being bent through prisms, and we can also study how light is being deflected off different objects. And we'll talk a little bit about that over the next couple of lessons. The other way then, it deals with light as a wave. So the concept of wave particle duality caused a lot of discussion in the past, and it's a whole topic in itself as well. This fact that light can exist as a particle and a wave caused an awful lot of debate. So if we think about like studying light from the geometry point of view, we will look at, I'm just going to introduce some terms as well that'll make it easier for us when we start to look at this. So what we can do is we can actually start to look at light and look at the path of light. So what we're looking at here, so if we focus first of all here on this object here. So first of all, we have our surface or object that the light is bouncing off. In this case, we have a mirror. We have the incident ray is the ray of light that's coming in. So imagine you have, for example, your light source is here, and what's happening is it's sending down a ray of light. Now you'll notice that these are straight lines. Light travels in straight lines. So this light that's coming in is what's known as when it's coming in, it's known as the incident ray. And what happens is it comes into contact with the mirror or the reflecting object, and it bounces off. And when it bounces off, it changes direction. And this is what's known as the reflected ray. It's the same ray, but essentially when it bounces off, we call it the reflected ray. Now, what we can do then is we can draw, so this incident point, or the point at where the light ray comes into contact with the mirror, for example, we can draw a perpendicular line up from this, and this is what's known as the normal. And then what that enables us to do then is it creates an angle. So the angle then that's created between the incident ray and the normal, this is what's known as the angle of incidence. Okay, and we sometimes we just abbreviate it with a small I. And then the other angle that's created here, so it's created between the reflected ray and the normal, is what's known as the angle of reflection. And one of the rules or laws in relation to light being reflected is that the angle of incidence is equal to the angle of reflection. So that's one of the laws. That's one of the laws of reflection. So you can say, laws of reflection. So one is that I is equal to R, and I represents the angle of incidence and R represents the angle of reflection. And two then is that all of these lines here, so the angle of incidence so this incident ray, this normal and this reflected ray, these all exist in the same plane. And what I mean by that is if we have a look here, so this represents the plane. So imagine it's just a section in space, if you like. So it's a two-dimensional surface. But this incident ray and this reflected ray they're all on the same plane, and this normal as well. These all exist on the same plane. Like if this light was to go, let's say, back this way, it would be in a different plane, and that's not the case. So they're the two main laws of the laws of reflection. One is that the angle of incidence is equal to the angle of reflection, and the other one is that the incident ray and the reflected ray, they all exist in the same plane. And remember, these are the laws that apply to reflection, and that's this process here, which is what we're looking at here. Like scattered light is a completely different thing. But what we're focusing on here is the law of reflection in relation to light being reflected like this, like what's happening here. So these here they're important kind of terms to learn as well. You know, the incident ray, the reflected ray, the angle of incidence, and the angle of reflection, and this normal as well. It's important that you understand these and that you can remember them as well and be able to identify them, you know, when you're looking at a diagram or something like this. But again, it's just, you know, you're kind of trying to visualize that. So this is just showing one ray of light, for example, but in reality there's going to be thousands and thousands of rays of light striking an object and reflecting off every second. But again, we try and simplify it and break it down so we can kind of get a model in our heads and understand and try and get a grasp on what's going on with light, for example, so we can build our models so we can actually study it. And this is something that you know, that can physically be shown and physically being studied as well. So this here is an experiment where you have a light source, and what's happening is it's creating like so this here, for example, the ray that's coming out of this light is what's known as the incident ray. I'll just put it here as I. This here is your mirror, okay, your reflective body. I'll just put it as an M. And then the light that's, see the way it's coming in, it's hitting here and it's bouncing off in this direction. So it's coming in this direction, hitting and bouncing off. This is what's known as the reflected ray. And then this line here that's been drawn on the paper, for example, this is what's known as the normal. And then what you can do is you can actually use a protractor and you can measure these, the angle of incidence and the angle of reflection as well. So this is something that can, you know, physically be done. You can actually see the light being reflected off. So hopefully that kind of makes sense, and it's just a quick introduction just to kind of introduce some key terms in relation to light, and it'll help us then as we move on and start to study light in a bit more detail. Okay, so thank you for listening.